Yes, so everybody, today we're still working with these rational expressions. Rational just simply means that it is a fraction, right? Rational means fraction. And so we're going to learn how to add those up. On our last lesson on this topic, we were multiplying and dividing fractions, and we factored and canceled stuff out. It was nice and easy. Remember multiplication, multiply across the top, multiply across the bottom. With addition and subtraction, it's a little different. And that's going to come into play when you think about how you add fractions like these. So, go ahead, jot these down, and it should be pretty simple. I think all of you can handle these pretty nicely on how do you add up two fractions. So think about what do you need in place to add fractions? Are you allowed to just add the numerators and add the denominators the way we could multiply? Spoiler alert, no, you can't. You have to change something before you can add those fractions. See if you can recall what that is and get that correct answer. See if you can combine those. Adding fractions. Both of these are pretty similar, you might notice. I just added some variables in them, letting you know, hey, it still works pretty much the same way, even with the variable. So just remember, you cannot just add the numerators and add the denominators. That does not work with fractions. Like if you have 1/4 of a pizza and you add 1/3 of a pizza, you do not have 2/5 of a pizza. You actually have more than that. No, you have less than that. No, you have more than that. We'll come back to that one. So in order to add fractions, we need them to represent the same portion. Basically, the denominators need to be the same. And so you want to get a common denominator. And I see a 2 and a 5. Denominator, those are the things on the bottom. And I want 2 and 5 to be the same number. And so the easiest thing is to see, well, does the smaller number, can I just multiply that by something to make it that bigger number? But does 2 go into 5 nicely? It does not, so we have to change both of these. And we want to change it into something called the least common multiple, or the LCM. So what's the smallest number that 2 and 5 both can go into or multiply to? Any ideas? 10 works, right? So I'm thinking I want to make both of these denominators a 10. And so on the left side, I'm thinking, all right, well, what can I multiply 2 by in order to make it 10? Well, I know that 2 times 5 is 10. So I want to multiply the denominator by 5. But in order to keep this equivalent, if I multiply the bottom of a fraction by some amount, I have to multiply the numerator by that exact same amount. Because now I'm not just multiplying by 5 on the bottom, I'm multiplying by 5 over 5. And hey, what is 5 divided by 5? Yeah, I know, it's tough. It's a 1. Are we allowed to multiply things by 1 without changing the value? Absolutely, we are. So now it's multiplication here on the left. That is the nicest and easiest operation with fractions. You just multiply those numerators together. 5 times 3 is 15. Multiply those denominators together, and we get 10 plus. On the right side, we have to do a similar process. I've got 2/5, and all I'm doing is I'm looking at that denominator. It's currently a 5. I want it to be a 10. So I know that I need to multiply that 5 by 2. Because 5 times 2 is 10. And in order to keep that fraction equivalent, I can't just multiply by 2 on the bottom. I've got to multiply by 2 on the top. Because 2 over 2 is equal to 1, and I'm allowed to multiply by 1. Does not change the value of it. When I multiply these fractions, 2 times 2 is 4. 5 times 2 is 10. Now we can add or subtract these fractions. They have the same denominator. And so if I have 15 tenths and I add 4 more tenths, how many tenths do I have altogether? Just add straight across the top, right? Once the denominators are the same, you keep that same denominator and just add the numerators. And 15 plus 4, that's going to be 19. Box that up. Now, if you have variables, it's still the same idea. I look at the denominators, and there's a 2 and a 5. The least common multiple is 10. Hey, ever wonder why it has to be the least common multiple? What if we go to a different multiple? What if I wanted to make those like 50? Could we do that? Would the problem still work, do you think? Yeah. Let's try that just for fun. 2, if I want to make that a 50, because I know 2 and 5 both go into 50. Yeah, it's going to be gigantic. If I want to make that a 50, well, 2 times what is 50? 2 times 25 is 50. I have to multiply that on top and bottom. I know this is crazy, but now you're going to see why the LCM is better. When I multiply those numerators, I get 75x over 50 plus, on the right side, to make a 5 into a 50, I have to multiply it by 10 on the top and bottom. 10 times 2x is 20x over 50. I know this is definitely overkill. When I add those up, they're both over 50. 75x plus 20x, that's 95x. It worked. I was able to add those fractions with a different common multiple. It wasn't the least common multiple, but it was a common multiple. But now if I look at that answer, 95x over 50, the numbers, like ignoring the x, I should have gotten 19 over 10. Well, what can I still do to that fraction, everyone? We can simplify the fraction. What number does it look like we can divide 95 and 50 by? They're both divisible by 5. So if we simplify this fraction, 95x divided by 5 would be 19x. 50 divided by 5 is 10. You see, we do get the same thing. So if you don't multiply by the least common multiple, or if you don't try to get the least common multiple in that denominator, the problem will still work. You're just going to have extra simplifying at the end. It's just making more work for you, okay? But we just need those bottoms to be the same. Those bottoms can be any numbers that are the same, but just in general, getting the least common multiple is just going to make it easier for us. It saves us a step or two in the end. All right. So what about adding true rational expressions? Like an actual rational expression is not only a fraction with a variable, but it's specifically when the variable is in the denominator. Okay, so if you got x down in the bottom, that's what makes it a rational expression. And to add or subtract rational expressions, same thing as fractions. You just have to get a common denominator. Good morning. So I even posed this question, hey, what's missing from the second denominator? So I want you to go ahead and try to add these two fractions here together. Now they initially have different denominators. Make those denominators the same, and then try to add them up, and let's see what you get. See if you can add those two fractions together. So hopefully you see those two denominators. There's a 3x and a 3. All right, so what does that second denominator need to make it the same as the one on the left? Just needs an x, right? That's what's missing. And so we can think of it as saying, all right, well, to make those denominators the same, we can just multiply that second fraction by an x in the bottom, because 3 times x is 3x. Then both denominators will be the same. They'll be common. However, if we multiply the denominator by an x, we'd have to multiply the numerator by x. So this turns it into 2 over 3x plus, well, 5 times x is 5x, and 3 times x is 3x. So I still have two fractions, but now do they both have the same denominator? Yes. Good. Yeah, that's right. That's right. They do. So we can add them up. When you're adding or subtracting two fractions, they have to have the same denominator, and you keep that same denominator. I always write that first. I always make sure I bring that denominator over to my answer first so that I don't get confused. Because sometimes when you're multiplying and adding, like in the same problem set, you might get confused and want to add those together and write 6x. But please try not to do that when you notice it's addition or subtraction. Just write that same denominator. In the numerator, 2 plus 5x. So should I write 7x up top, like when I add those up? No, we can't do that, right? Those are unlike terms. One has an x, one does not. One's a constant. So we just write this as 2 plus 5x. Right? We still need to keep them as two separate terms because we can't combine them. They're not like terms. They would both need to have an x, or they would both need to be constants. Then one last thing, once we add them up, see if we can simplify it. I see an x on top, x on the bottom. Can I just cross those off? Ooh, we're not too sure about that one. Remember, like we spoke about in our last lesson, that numerator is kind of like locked in. It's a bigger polynomial. That x is part of a larger polynomial, so I can't just cancel out part of one of those with something on the bottom. Right? X isn't its own separate factor. That whole factor up top is a 2 plus 5x. That's one thing. It's one entity. It's one factor. So I can't cancel that out with just the x on the bottom. So this would be our final answer. And that's totally cool. We had two fractions. We now have one fraction. Da-da-da. We added. And that's the lesson. Pretty nice, right? Is it going to get more difficult, do you think? What? No, not in my class. That's, well, maybe. All right, so we're still going to use that same idea of trying to get the denominators to match. And this looks a little complicated, but to add these up, just look at the two denominators. And we want them to be the same. I want the left denominator to be exactly the same as the right denominator. And we're essentially going to look at each base separately in the denominator. So I mean, like, look at the coefficients. I want those to be the same. Look at the a's. So I want there to be the same amount of a's in both denominators. And then look at the b's. I want the same number of b's in both denominators. So if one fraction is like a to the fifth, the other one also would need to be a to the fifth, or whatever we decide on. Oops. Whoa. So let's start by trying to make this left denominator look like the denominator on the right. And just start each base at a time. Let's start with the coefficient. That's a 5. Over here is a 3. 5 and 3. This is just like a regular fraction. What's the least common multiple of 5 and 3? 15, right? 5 times 3 is 15. So I know that I need to multiply this 5 by how much? By 3. So I know I'm going to multiply by a 3. Now, look at the next base over. That's an a. How many a's do I currently have on the left? Just one of them. How many a's are on the right? Two of them. So how many more a's do I need on the left side? We need one more, right? Just one more a, then they'll both have a squared. They'll both have two of them. So I'm just going to multiply by one additional a because there's already one there. When I multiply those together, a times a, that'll become a squared. So it'll be the same as over there on the right. Now b's, I've got b to the third on the left. On the right side, there's b to the second. Do I need to bring in any more b's on the left? No, we don't need to bring more on the left. We'll need to put another b on the right side, won't we? Because there's only two on the right. But the left side already has enough. It's already got at least as many that are on the right side. So all this fraction on the left needs is a 3 and an a. But just like our regular fractions with just numbers, if I multiply the denominator by 3a, we have to multiply the numerator by 3a as well. And now before I actually multiply those together, let's go to the right side and take a look at that second fraction and make sure that we can get it to match up with the same denominator as well. So what are we going to multiply this by? Again, let's look at one base at a time. Starting with a 3, we already said that we need an LCM of 15. So 3 times what number equals 15? 5, right? Okay, now look at the second base. That's an a squared. Do I need to multiply this one by any more a's? No, because the left side, it needed one more. It's going to become an a squared. I already have an a squared, so we don't need to multiply by any more. We already have more than that other side has. Finally, look at the b's. This is b squared. On the left side, there's b to the third. So how many more b's do I need to multiply by on the right? Just one more, b to the first power, or just a b. If we multiply the denominator by 5b, we have to multiply the numerator by 5b. Now we have two multiplication problems. Remember, those are the best. Those are the easiest. Just multiply the tops together and the bottoms together. So when I multiply, I'm just working on the fraction on the left right now. 3a times 2x. We're going to multiply the coefficients together first. Those are those numbers out in front. 3 times 2 is 6. And then when I multiply the variables together, a times x, you just write them right next to each other. A times x, that's just ax. It's just an x. In our denominator, we're going to multiply all the common bases. So like the coefficients first get multiplied together. 3 times 5 is 15. And that's what we wanted. We had earlier established that we're going to have an LCM of 15. That's what we were going for. When I multiply the a's, 1a times 1 more a, that would give me a squared. Make sure when you're multiplying, you're changing the exponent, not the coefficient. A times a is not 2a. A times a is a squared. And then b didn't change at all, so that's still just a b cubed. Are we okay so far? Trying to get this common denominator here, just with some letters. Plus. So let's look at the fraction on the right. Start with the numerator. Up top, we have 4y times 5b. Multiply the coefficients first, those numbers in front. Let's just say 4 times 5 is 20. And y times b, that's yb or by. Order doesn't matter. Generally, I try to write it alphabetical. If not, no big deal. I'm never going to take off points for that. And our denominator, well, we should get the same denominator as the left, but let's just double check to make sure that we did multiply by all the correct components. First, we had 3 times 5, and that's 15. All right, so far, so good. Then there's an a squared. There are no other a's to be multiplied with, so you just bring that a squared along for the ride. And then finally, you've got a b squared times 1 more b. If I had 2 of them and I multiplied by 1 more, we've got a total of 3 of those, so b to the third. And before we add them up, quick check, do our two denominators match right now? They have all the exact same terms, same exponents, same variables. Yeah, it looks good to go. 15a squared b cubed for both of those. So our denominators match, so just carry over that exact same denominator. Don't add them together, just rewrite it. Always start with the bottom. Keep it the same. We don't want to accidentally change that. Now the numerator, this is actually the easiest part. 6ax plus 20by, are those like terms or are they different terms? Do they have the same variables or do they have different variables? Different! Good, good, yes, that's right. A and x are different than b and y. Good morning. So we just actually write them out next to each other. 6ax plus 20by. Those are not like terms. We can't combine them. This is our fraction. To determine if we can simplify anything in our fraction here, look at all the terms. We have 3 terms together, right? 2 in the numerator, 1 in the denominator. Is there something that I could divide all 3 of those numbers by? 6 and 20 and 15, are they all divisible by the same number? Can I divide 6 and 20 and 15 by the same number? Unfortunately, we cannot. Close, close. Good morning, I know. Morning math is tricky, isn't it? And then they all have different letters. None of them have the same letters. So this is it. We've simplified it all the way, or there's no more simplifying we could do, I should say. And that's adding fractions, adding rational expressions, I should say. Any questions yet? Not too bad, right? This is great. I'm sure it's this easy the whole time. Yeah. Can't get more complicated. So let's just practice this, everybody. Here's example 1. I want you to try this on your own. Only difference for this problem is look at the sign in the middle. It's subtraction. Still the exact same idea. Get yourself a common denominator and then combine them. So look at the 2 denominators. Ask yourself, what's missing? What does one denominator have that the other one doesn't? And you want to make them the same. So try to make those 2 denominators match. I want everyone to give this an effort right now. This is where learning comes in. By trying. We can't be afraid to make a mistake, otherwise I'd never step in front of this board to teach you. That's what we learn from. Make those 2 denominators the same. What's missing from the right side and what's missing from the left side? Keep going, keep going. Get them the same. Then combine them. Mm-hmm. Good, good. I like what I'm seeing. Excellent. Yep, match them up. And once those denominators are the same, make sure they have the same variables with the same exponents. So we need like one more there, right? But if you put on the bottom, you have to put it also up top. It's okay, it's okay. Morning math, right? Yeah, all right. Got the right denominator? Yep, that's a good denominator. That's a good denominator. Yes, that is a good denominator. Okay. Let's take a look at this together. So starting on the left side, think about what do I need to multiply this denominator by to make it look like the denominator on the right. So like what's missing from the left that the right side has? What does the right side have that we don't on the left? A y, right? There's a y over there. There's no y over here, so I'm going to multiply by y because I need to make sure that it's got everything that the dude on the right side has. And what else? That right side has an x. Do we have at least one x on the left already? We do. We got more than that. We got plenty of x's. So I don't need to multiply by any more. And that's all that's on the right side, 1x and 1y. We made sure we have at least 1x, and now we have that 1y. Multiply it by the top and the bottom. All right, so we took care of fraction on the left. Now we have to take a little stroll, check out the dude on the right, and we're going to do that same process. So right now, we're chilling with 1x and 1y. Look on the left side and see what fraction on the left has. Well, first, I see that there's a 3 on the left. Do we have a 3 on the right side? We don't have a 3, do we? We need one of those. So I'm going to multiply by a 3 because the left side has a 3, and we don't have a 3 on the right. So I'm going to multiply by a 3. Now look at the next base over there. I see an x to the third. Do we have an x to the third? No. We have 1x. So how many more x's do we need? We need 2 more, right? Because then if I had 2 more x's, we'd have a total of 3. Then we'd match. We'd have everything that the fraction on the left side has. So I'm going to multiply by x squared. That way, we make sure that we've got the same thing that the left side has. And there's nothing else over there. So we multiply by an x squared, a 3x squared on the top and on the bottom. Okay, now we're going to rewrite each of those fractions after we multiply them out. So on the left, 4y times another y equals 4y squared. And the denominator, y times 3x cubed is just 3x cubed y. Just put them right next to each other. Then we have minus our second fraction. Multiply the numerators together. 5 times 3x squared is 15x squared. And our denominator, I look at the coefficient first. There's just a single 3, so that 3 we'd write first. X's, multiply all the x's together. X times x squared gives us x to the third. Then there's a single y. It just comes along for the ride. And before I add or subtract in this case, do our denominators match? Are they the same? Yes, they are. So we are good to go. I'm going to write a single fraction bar with that exact same denominator. I always do that first just so I don't accidentally combine them a way I shouldn't, like write, oh, that's 0. Don't do that. And the numerators, we've got a 4y squared. And just make sure that's a minus sign, right? That's really the only difference for subtraction versus addition. It's just a different symbol in the middle. Nothing else is really going to happen. Minus 15x squared, because those are still different terms. They have different variables with different exponents, so we can't combine them. Look at all 3 terms carefully. Is there a common factor that all of them have that we can divide all 3 of those by? And no, there is not, so this is it. That is our final answer. We have subtracted 2 rational expressions, and we now have a single rational expression. Questions? Awesome. Do you have a broken pencil?
Multiple, actually.
Do you like to put them between your fingers and pretend they're claws?
Yeah, like Wolverine.
What?
Yeah.
All right, here's where we are really going. Trinomials, polynomials, bigger denominators. So initially, looking at this problem, let's jot this down in our notebook first, because I know that there's a lot to write. There's like 8 different terms here. So go ahead and jot this down. And for those of you who like writing words, Here you go. So you have x over x squared plus 5x plus 6 minus 2 over x squared plus 4x plus 4. So this is the real type of questions that we want you to be able to add and subtract. Now, initially, looking at these, you might be tempted to say, okay, well, I want to make the denominators match, right? We obviously want to get a common denominator. But here's where you have to be careful. You can't just say, oh, x squared, those match. 5x, oh, I'm just going to add an x here. Oh, that's a 6. Let's just add another 2 there. You can't do that. You can't add into like the middle of something. That changes it. That doesn't work. These are polynomials, and something that I've been trying to stress to everyone throughout this unit is that whenever you've got a rational expression or a fraction with multiple terms that are being added or subtracted, you have to consider them like inside of parentheses. Like that's one thing. That's one number. If I plugged in a value for x, I would perform all these calculations first. I'd square that number, I'd multiply it by 5, I'd add 6, I'd add those up, right? And then I get my number. Then I could compare it to the numerator and see if that simplifies or divides out. Same thing here. I want you to write parentheses around those just to try to remind you that I can't take out like an individual term from a larger polynomial. You have to think of it as one thing, one entity, one piece, one factor. So then if that's one single item, one single denominator, and I want them to be the same, you might be like, oh, so I've got to multiply this entire fraction over here by an x squared plus 5x plus 6. Good news is no, you don't, because that would be some crazy multiplying, right? Instead, we're going to do something that we did with addition and subtraction, and something that we do to make multiplying and dividing back on in our previous lesson. To make things simpler and smaller and more manageable, what do you think we should do to both of those trinomials first? Factor. Yeah. Can we factor those? We can. And by breaking them down into their individual factors, the little pieces that make each of those up, we're going to see that they actually already have some things in common. So we don't need to multiply by additional things to get that common denominator. They already have some overlap, but we just have to look at the individual pieces, those individual factors. So this first denominator on the left, I'll do this one in green. We have an x on top. That can't be factored. But the denominator, are there two numbers that multiply to 6 and add to 5? 2 and 3? Looks good to me. So I'm going to write x plus 2 and x plus 3. So this whole unit 8, factoring is your friend. That's always the go-to thing for any rational expression, for any type of operation we're doing. You always want to factor first. Over here on the right side, well, first off, it's subtraction. The numerator is just a 2. Obviously, we can't factor that. And then the denominator. Two numbers that multiply to 4 and add to 4? Is that possible? Help me out, Slim. What are we going to do? What? A 2?
Yeah.
But we need another number.
A 2.
Another 2? Is that really? What? Does that work? X plus 2 and an x plus 2? Yeah, I think that works. Good job. I'm proud of you. All right, so we've got these factored. That's great. We still have two fractions, but I want you to look at each factor or each set of parentheses as its own like term in the denominator, kind of. And I want them all to have the same factors in each denominator. So start on the left side here. I have an x plus 2 and an x plus 3. What's missing from the left side that the right side has? So look at the right, look in purple. It's got an x plus 2. Do we have an x plus 2 on the left? Do we have one? We do have one of those x plus 2s, right? That's fancy, that's awesome. So it's like, check, I've got that one. But what else is on the right side? Another x plus 2. Do we have a second x plus 2 on the left? No, we do not. So we need to make sure that it has an extra x plus 2. So what we're going to do is just multiply by another x plus 2 because they need to have the same factors in both denominators. And if I multiply by an x plus 2 on the bottom, we have to multiply by an x plus 2 on the top. Now, if you haven't started doing this yet, this is going to be the unit that you are going to want to always put parentheses around these, right? Don't just leave x plus 2 floating like that. You want to make sure that you put in parentheses to remind you that that is one entity, that's one factor, one grouping that sticks together. All right, now on the left here, do we have everything that the right side has in the bottom? Like the right side, it's got 2x plus 2's. Do we now have 2x plus 2's on the left? We do. So we're good on the left side. Now we have to take a stroll over to the right side. And let's check this out. So look at the left side in green. It has an x plus 2. Do we have an x plus 2? For sure, yeah. We've got that. I already have an x plus 2. But what else is over there? There's an x plus 3. Do we have an x plus 3 on the right? We don't. We need one of those to match it up. So we're going to multiply by an extra x plus 3 on the right side because the left side has one of those in the denominator and we don't on the right. If we multiply the bottom by x plus 3, we have to do that up top. So now, do both denominators have all the same factors? Yeah, they both have 3 factors, 2x plus 2's and 1x plus 3. They are the same, so now we can go ahead and add or subtract them. Now, in the numerators, make sure you multiply those out. So that's where the actual calculations are going to be coming into play. So take this x, and I'm going to distribute it to each of those in the numerator. X times x is x squared. X times 2 is 2x. And this is all over x plus 2 times x plus 2 plus x plus times x plus 3. Is there a way I can kind of combine or write this a little bit nicer? Yeah, if I have an x plus 2 and another x plus 2, that's the same thing as x plus 2 squared. It just saves us a little bit of writing that way. Anything times itself, you would just square. Here, so everyone can see that, x plus 2 squared. And then you have another x plus 3. On the right side, look at those numerators. A 2 times x plus 3. I'm going to take that 2 and distribute it to each term in those parentheses. 2 times x is 2x. 2 times 3 is 6. This is over that exact same denominator, right? It's got to be the same. X plus 2 times x plus 2 is another x plus 2 squared. And there's one more x plus 3. But there's one thing we've got to be very careful with at this point. And that's the subtraction sign. I am subtracting these two numerators. What should we do on the right side to make sure we're subtracting correctly? I shall show you. Remember me talking about parentheses, how important they are this unit? I said it like a minute or two ago. Make sure you've got that in parentheses also, because when I do in my next step, combine those and write it as like one fraction, we subtract the numerators. I'm actually not just subtracting a 2x, I'm subtracting a 2x and I'm subtracting a 6. So we're going to be subtracting both of those terms. The 2x plus 6 are both being subtracted. And so we're going to be like distributing that negative sign to each of those terms. And that's where so many students, well, forget about that subtraction. If it's addition, no problem. You're just combining like terms. But in this case, we do want to be careful. So they both have the same denominators, right? They match now. So we can write this as a single x plus 2 squared x plus 3, right? It's the same denominator. But now in the numerator, are there some like terms? Well, starting on the left, I have an x squared. Are there any other x squareds up top? No, so I'm just going to bring that x squared along. Now, I have a 2x, but I'm subtracting another 2x. So it's like I'm distributing, and this is a negative 2x and like a negative 6. If you want, change it to a plus and flip the signs of everything to the right of it, if that helps you. And if I had a positive 2x and I subtract 2x, I have 0 x's. Those both would cancel out. Then last, I am subtracting a 6, so I'd write this as minus 6. So you have x squared minus 6 over x plus 2 squared times x plus 3. And just to get in the habit, put some parentheses around this, just to be safe. I know we're done calculating and all, but we just need to get in that habit right now at this point. Hey, that numerator, could I actually write that as an x plus 3 and an x minus 3? We can do that, right? And then cancel out the x plus 3's? Or can't we? Is that the difference of squares? Yeah, is 6 a perfect square? Oh, it's not. Oh, I tricked you, didn't I? Gotcha. Wolverine's so easy to trick. He's like, well, I can scratch it with my claws.
Exactly what I was thinking.
Yes, sir. What? Is it okay if it's a different color? Or is that worse?
No.
All right. So then box it up. That is our final answer. Pretty fun, right? Yes, it is. I know. We get to exercise our brains in the morning. So much better than exercising our bodies, right? Like we could go for a run outside in the cold, or we could do math. Like honestly, what would you rather do at 8 a.m. on a Friday morning? Why did so many of you say that? Like when I ask you a question like, what's 2x plus 3x? It's silent. But if I'm like, you want to run the cold? You're like, yes, if it gets me out of this classroom. Like all of you answered. I don't understand. I'm trying to make this easy for you. Oh my gosh. All right, so try this one on your own, everybody. Note that it is subtraction. When I write this down, I would highly suggest writing parentheses around every one of those numerators and every one of those denominators. And where that previous problem, we were factoring trinomials, these are binomials. And take a look at those denominators. Can we factor those two? Those two denominators, are they factorable? Can we break them down? We can, just like we went over at our last lesson, using GCF, right? Take out the greatest common factor in each of those denominators. Remember that? Now?
Exactly what I was thinking.
You had no clue, did you? You're like, What multiplies to 12 and adds to 4? Oh, Wolverine. He's such a kidder. He's pretty much like a clown, you know, with like ridiculous hair. Do you know anyone else in this class with ridiculous hair? I didn't say anything. No, I wasn't implying anything. What? You can do it. Hey, that's good. That's good. You don't have to be perfect. You just have to give it an honest effort right now. Don't be afraid to make a mistake.
Just multiply it by 2?
Yes. Yes, exactly. Once you factor those two denominators, think, how do I make them the same? What do I need to multiply one of them by to make the other the same? Yeah, but before you do that, you want to break it down and factor it to make it smaller to see those individual parts. So like, what do these... Yeah, exactly. And over here, you can actually take a... Yeah. So write it like that, and then compare your two denominators and see, okay, how do I make them the same? What do I need to multiply one of these by to make it the same as the other? Oh, look at that. Yes. Can you? So how many terms do you have altogether in that entire fraction? 4, right? 2 in the top, 2 in the bottom. In order to simplify that fraction, every one of those 4 terms would have to be divisible by the same number or by the same variable. So can that be simplified? No, right? So that is the final answer. You're good to go. What do these two have in common? Yep. What do those two have in common? Bigger. GCF. Yeah. So you're going to bring that up front and then write what you have left over. Bring the 2 out in front, write what you have left over. Yep. What over here? One more time. So now look at your two denominators. What do you need to do to make them the same? Okay, how? Yeah. Yeah.
Just that?
Yeah.
Whoa.
Isn't that nice? Pretty cool. Oh, so these denominators, we want to factor them, right? Break them down. There's not 3 terms, only 2. So we're going to take out the GCF. What do both those have in common? So think, what could you divide them both by? These 2 numbers in those parentheses. Yeah, so you'd bring the 2 out in front. And what would you have left over after you divided out a 2 from each of those? Yeah. And do the same thing over here. What's going on over here? That doesn't seem like something Slim would do.
I have my one mechanical.
He's like a, I mean, he's a leader. He's a Boy Scout. Cyclops is.
I wonder where all these pencils came from.
Or have been coming from all class.
It's like a vandal.
Hold on. So I took the 2 out of here.
Yeah.
And then I multiplied this by 2. And then.
Looks good to me.
Okay.
But then you could still
factor
multiply or combine like terms.
Okay.
So since it's subtraction,
Yeah.
you'd be subtracting both of those terms, just like we did in that previous problem where I kind of distributed the negative sign and then combined like terms.
Okay.
So hopefully all of you were able to look at that first denominator, 2x minus 6, and we want to factor it, meaning break it apart into smaller pieces and see that, oh, that's the same as 2 times an x minus 3, right? Remember that GCF factoring? Taking that out of each of those? 4x minus 12, those have a common factor of 4, which leaves us with x minus 3. So these are my two new denominators. In order to subtract those two fractions, I need them to be the same. Now, they're pretty similar, aren't they? They're very, very close. 2 times x minus 3, 4 times x minus 3. If I want them to be the same, what's the only thing I have to do to make them identical? On the left, this just needs to be multiplied by another 2. Because 2 times 2 is 4. Then wouldn't those two denominators be the same? You'd have 4 parentheses x minus 3. On the right side, you have a 4 parentheses x minus 3. So we're just going to multiply by a 2 on top and a 2 on the bottom. Keep those parentheses, though. So then in my numerator, I'm going to have 2 parentheses x minus 5 minus parentheses x minus 7 all over this same denominator of 4 parentheses x minus 3, because they'd have a common denominator at that point. I can write it as one single fraction. We had 2 fractions, now it's 1. But there's still more we can do in that numerator, right? We didn't actually do any calculations. We need to distribute, we need to simplify, we need to combine like terms. So I'm going to distribute the 2 to each of those, and I'm going to distribute the negative to each of those. It's still going to be a 4 parentheses x minus 3. This gives us 2x minus 10 minus x plus 7. So everybody see where I got those 4 terms from? By distributing the thing that was in front of the parentheses. So I distributed the 2 to the first 2 terms, and I actually distributed the negative sign to those other 2 terms. And now that we got rid of all the parentheses in the numerator, are there some like terms that I could combine? Up top? Do we have some like terms? Yes? No? Yeah? We don't know? If I had 2 x's and I subtract an x, I'm left with 1x. What's negative 10 plus 7? A negative 3. That leaves us with 4 parentheses x minus 3, and we're all done, right? Uh-oh. Wait a minute. Can I put parentheses around those? Is that okay? Yeah. Hey, what else can we do, everybody? That's right. That's kind of nice. That's going to, simplify. And it leaves us with nothing over 4. Do I put a 0 up top then if there's nothing there? No, we want to always do a 1 for a fraction, because 0 divided by 4 would be 0. And that 4 would be pointless, but in this case we put a 1, because anything divided by itself equals 1. So that's the same as 1/4. Nifty. Aren't you glad that not everything canceled out this time? Wouldn't that have made you a little angry? Like, remember that one problem? Oh, that was so fun. That last lesson. No, you don't even remember. You blocked it. It was so mean. All right, we feeling okay with this? I mean, there can't be anything more, can there? No. You getting nervous? We have a whole half an hour left. Oh, what is that? Black magic. Oh, that looks crazy. Man, I gotta bring fractions into this. Ugh. Did you wish I stopped on the last slide now? This is now kind of combining our 2 lessons from this week. Multiplying and dividing with adding and subtracting. So go ahead and jot this fun little puzzle down. And we're going to figure out, all right, how do I write that as a single fraction? This is called a complex fraction because, well, look at it. It's a complicated fraction. On our last lesson, the first one this week with multiplying and dividing, remember what we do if you're dividing by a fraction? How do you rewrite it? Anybody recall? Yeah, the reciprocal, and you multiply by it. But that only works if there's a single fraction in the numerator and a single fraction in the denominator. Do we have just one fraction in that denominator right now? No, we have an x and then a minus x over 6. That's not one fraction. So what we want to do for both of these is make them both into single fractions. So this is our big fraction bar, and let's just look at the numerator, where I've got an x plus 3. I want to make that into one fraction. So like we can think of this as x over 1. Right? It's its own fraction, x over 1. You typically don't write that, but it is. And so just look at that numerator. I have x over 1 plus x over 3. If I wanted to combine those two fractions in that numerator, what would I have to multiply this guy on the left by? A 3. Right. I wanted to have the common denominator of a 3. So I'm just going to multiply by a 3 on the top and a 3 on the bottom. So now this numerator, 3 times x is 3x. 3 times 1 is just 3. Plus the fraction that was already there, that x over 3. So I'm just looking at just that numerator. And now that these have a common denominator, those two fractions that are being added, I can combine them and write them as one single fraction. 3 on the bottom plus another 3 on the bottom. I'm going to have 3 on the bottom, right? That's the common denominator, kind of like what we've been working with all class. Now just add the numerators. If I had 3 x's and I add one more x, how many do we have altogether? There's 4 of them. There's 4 x's. Okay, now remember, that was all just that top fraction. We had those two different terms. I combined them to make it into this single fraction now. Let's do the same thing with the bottom fraction. X minus x over 6. So think of this x over 1. What do I need to multiply that by to get a common denominator? Just a 6, right? The other fraction has a 6 in the bottom. We don't on the left, so I'm just going to multiply by a 6 over 6. That way they'll have that common denominator, and I can just write it as one fraction. So 6 times x is 6x. 6 times 1 is 6. Then that second fraction, the minus x over 6, stays put, right? I didn't change that second fraction. It was fine. But these two have a common denominator now. So when I write my fraction over here, I put it over 6, because that is the common denominator of those two. Now look at its two numerators, and it's just subtraction. So if I had 6x and I subtract one of those x's, how many x's do we have left? There's 5 of them. Very good. 5x over 6. Does this look a little bit nicer now than what we started with? This is just like a problem we did back on Monday. You're dividing by a fraction. So this blue fraction that's being divided by, we're actually going to change that into multiplication. Right, so I'm going to bring it up here. I'm going to multiply by the reciprocal of 6 over 5x. Remember doing that? Like dividing by one fraction is the same as multiplying by its reciprocal. So I flip that fraction, or what was it? Keep, copy, keep, chop, change, copy. Yeah. Okay, good. I'm glad you could understand me because I couldn't understand myself. And now you're just multiplying across the top. 4x times 6 is 24x. 3 times 5x is just 15x. Anything else I can do? Divided by 3 and an x, right? I can simplify that. 24 and 15 are both divisible by 3. 24 divided by 3 is 8. 15 divided by 3 is 5. And then divide them both by x, right? There's an x on top and an x on the bottom. So like those would both cancel out. No more. Slim is a genius. So that's 8/5. Awesome. Aren't fractions fun? Remember how much you used to hate them? Now I bet you love them.
Exactly what I was
They're so easy.
These are the best.
Yeah, they're so many things you can do with fractions. Combine them, you can change them, you can flip them. Oh my goodness. This is amazing. Anybody have a question on like any of these steps where you just weren't sure why I did something, or like where did that 6 come from, or how did you get that 5x? Anything like that at all? I want to make sure that you've got these steps down in your notebook and that you understand what's going on. Ready to try one on your own? Take off the training wheels? Yes. All right, this is it. Whoa, 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 hold on. No, look at that closely. I was nice to you. Do you see that in the numerator? Right? And look at the other denominator in the bottom. Come on. Wasn't I pretty nice? You're welcome. I'll make this a little bigger for you, though, so you can see how super nice I am. Is it easier to see it on this screen? That's awesome. And then since this has an x on the bottom, this one doesn't. I want to make sure that you multiply the top and bottom by an x also, because you need both those denominators to be the same. So much fun, right? Yeah.
There's no x on that.
Well, you can just simplify the numbers.
Okay.
That's fine. And then you just leave that x on the bottom. So you want this to be the same as that. So think, what do I need to multiply this by to make it exactly the same as that?
So then just like
A 2 and what else?
okay.
Yeah, exactly. Okay.
I made it the whole. Oh yeah.
You can simplify that numerator.
Oh yeah.
And then you'll, then like at this point you have one fraction over another fraction. So go ahead and flip.
After that, would I make that? Or no?
Oh, you
Just
totally,
that?
yeah, you can. That's fine. Either way, it's fine. Like we'll want to do that at least in our, like near the end after you make it into a single fraction to see if something does cancel out. So you can do that now,
And
or you
then
can do that later on.
you get this.
Yep.
And then that, and then what do you do?
So dividing by a fraction is the same thing as multiplying by this reciprocal. So I always think of it as like, think of there being like a pin in this one. That one's stuck in place.
Mhm.
And this one's going to pivot. It's going to kind of
Copy
swing.
transfer.
Yeah, exactly. It's going to swing around and go upside down next to it.
Yeah, so forward.
Yes. And the 2. All right, hold on. I told Wolvie that I'd take a look at his.
I'm factoring this. Is it just a 0 over here then?
If you take,
If I'm factoring that, would it be a 0?
what are you factoring out?
I don't need to factor that, do I? The x squared minus 6x. Do I factor that in now?
Oh, yeah, you can. Yeah.
Then it's got to add to 0 then, right?
No, you're not going to, like, divide it out. Like, if you have x squared minus 6x, you wouldn't just write x minus 6, because that's a different value. You have to keep it the same by keeping that out in front. Now they're identical. Now they're equivalent, right? You're just rewriting it. You're writing it a different way. They're still equal to the same amount. I think that looks good. Yeah. Yeah, what? Wasn't that bad. Come on, Slim had a question like 100 years ago. Yes. You got a question, Alex?
Yeah, so this would be 6 to the third. So do I add it or multiply it?
Multiply. Because you have like an exponent to an exponent. It's
Okay,
multiplication.
So then that equals 3. So there's 9.
Yep.
But then these cancel, and then you put that over there.
Ooh,
And
what
then it's
cancels?
3. Oh, wait, no, that equals
They
6.
don't cancel.
This is what I have. Will that be like times?
Yep, right. Because then when you multiply those, you'll get the same denominators. And you can then write it as one fraction.
And then you get this.
And so now you have the same denominator. So write it as one fraction with 4x on the bottom. And then this would be up top, the 2x minus 6. Now it's one fraction. Good. This is correct. Now, dividing by one fraction is the same as multiplying by the reciprocal. So leave this fraction here. Take this one and kind of like swing it around. Move it upside down and put it right next to that. Yes. Yep. And now you're just multiplying the tops, multiplying the bottoms. Yeah. Good job.
I don't think I did the rest right.
This actually is going to be an x squared because you're multiplying x times x gives you x squared. So just go back to this step. It's good up to that point. Nice job, Joy.
I think I did it really wrong because everyone else got something different than me. But like I did the same thing you did here.
Okay, so look at this numerator. 2x minus 6. See how that 6 doesn't have an x?
Oh, you can't even do that.
Right, so you're going to leave 2 terms in that numerator. Everything else, though, is good. Yeah, it is.
Yeah.
Yes. Yeah. And now, what do... Oh, wait, this should be 60. 15 times 4 is 60.
I had to use the
We're still working?
I don't know. I got that mess up here.
This is correct. Here, you're multiplying 3x times 2 is 6x. But then you'd have to distribute the 6x to both of those terms. You'd still have 2 terms.
To that.
Yes. Yeah, keep going from there, okay? So it's this right here. 2x minus 6 is not 12x.
Oh.
This is right.
Yep.
And then it's over 60.
Yep.
All right.
Oh, and then there'd be an x with the 18, right? Because you're distributing the x as well. And now, can you divide all 3 of those terms by something? I really like what I'm seeing, everybody. By the way, I'm pretty sure this is the last slide. Yay. So we have 15 minutes. Let's pop open those Chromebooks, start cranking through some Delta Math to make sure we really got this down pat. I'm going to go through this problem for anyone who may have gotten stuck somewhere, or just wants to like reaffirm that they're doing their steps correctly. I'm going to work through that. If you already got it, 10 over x minus 3, you're good to go. I don't know, did you break any pencils today?
I didn't bring any today.
Did you try litter your broken pencils on someone else's desk?
I would never.
Yeah?
Slim simply took
If
it
you need to go to the restroom, that's fine. You can right now. Yeah, you can go fill up your water bottle. That's fine. Only one person at a time. All right, so looking at just the numerator fractions, there's already a common denominator. So 8 plus 7 is 15 over 3x. In that denominator, though, I've got a 4x here. This is only a 2. I want them to be the same. So I'm going to multiply by another 2x to make them match. So if this 2x times 2, that would equal a 4x. Then it would be the same. So I'm going to take a 2x times 1 up there. And then I've got a 2x minus 6. So that's 2x minus 6. Those are not like terms. I can't combine them. And now it's over a 4x. So that's your first step for one of these complex fractions. It's to get it so there's one fraction up top, one on the bottom. Do you see that, how we can't combine those?
Yeah.
I know, you want to be like, oh yeah, just subtract or multiply or whatever. You okay with that so far? Yeah. So you have a common denominator of 4x. So you just write it as one fraction, 4x, with those two terms up top. Now that I have one fraction divided by another fraction, I'm going to multiply by the reciprocal. So I take this fraction on the bottom, I'm going to flip it upside down. So instead of the 4x being on the bottom, 4x is going to go in the top, right? I'm flipping that bottom fraction upside down. The 2x minus 6, that was in the numerator of that bottom blue fraction, is now the denominator. And these two are being multiplied. Okay, dividing by one fraction is the same as multiplying by the other. Yeah, we totally could. Right? Did anyone else recognize that? 15 divided by 3 is 5. You could write this as 5 over x, and you'll get the exact same thing. Absolutely. It'll give you smaller numbers, too. It'll be nicer to work with. And then when you multiply two fractions, just multiply the tops together. Then you multiply the denominators together. Yes, you have a question? Get out of here. 15 times 4x is 60x. That denominator, I had to distribute the 3x. Shoop, shoop, times each of those. That gives us 6x squared. Make sure you remember that x times x is x squared minus 18x. And then at this point, this fraction has three terms. Is there a common factor, something that I could divide all three of those by? Brenna? That's only addition and subtraction. Remember, multiplying, anything goes. You multiply any numerators with any denominators. It's super nice and easy. Like, we love multiplying fractions. 66 and 18 are all divisible by 6. And every one of those three terms also has an x. So I'm dividing everything by 6x, which leaves us with this. And then Connor, you had said that you changed this to just a 5. And so when you multiply, you'd have 5 times 4x, which would give you 20x, right? Over, then here you would just distribute the x. So you'd have 2x squared minus 6x. Did you get that? And then simplifying those, well, 22 and 6 are all divisible by 2. So 20 divided by 2 is 10. 2 divided by 2 is 1. And then 6 divided by 2 is 3. And then they all had one x available. So you take one x out of each of those terms, basically. And you should still get the 10 over x minus 3. Anyone want me to take a look at their work at all, or anything you were perhaps unsure about?
I never got to 20 or 60. I simplified this too. Is that a-
As long as you simplified this term as well,
Yeah, and I did.
which you did. Good. I just didn't see the crossing out there. But yes, you absolutely are allowed to do that. As long as it's every term in the numerator and every term in the denominator, that is allowed. You couldn't have just done one term up top at the bottom. Sure. 1 second.